Hi, welcome back. Today we're going to take a look at related rates and how they apply in calculus. Now, if for those who want to know what a related rate is, you've probably heard about them before from your older brothers or sisters. Frequently, we're trying to, in a math problem, like in a physical problem, we want to establish a connection between rates of change. Now, we abbreviate rates of change, you'll hear us call it the ROC. But anytime basically you hear the phrase rates of change or anything dealing with change or rate, we're really talking about a derivative. A related rate measures the change of a derivative of something in regards to an independent variable t. Of course, this should sound similar to what you did in parametrics last year. This t is what you would call a parameter. And what's nice about parametrics is that it makes x and y independent from each other. And that's what we really like about parametrics. And we can use them in calculus to find how fast a radius is increasing or how fast the volume of a tub might be increasing as water is being poured in. So to give you an idea how parametrics apply to this, we might recall last year we would say like let x be a function of t, like x would be like f of t, and we could say we'll let y equal a function of t as well. Whoops, sorry, don't want to be f of t again. We might let y be a function like g of t. So if I took the derivative, remember x is a function of t, the derivative of x in Leibniz notation would be dx dt, would be f prime of t. Same thing with y, because y is not a function of x. When I take the derivative of y, it is a function of t as well. So we would get dy dt is g prime of t. And we can use this in parametrics, in related rates to answer a whole slew of really interesting questions about instantaneous changes. So let's take a look at our first example. In our first example, we are given this parabola, y equals 5x squared minus 6x plus 2. We want to find dy dt. So let's talk about what this means for us. If we think of y as being like our vertical axis, dy dt would be the change in our vertical axis over t. So if we picture t as being like time, you're looking for the change in y over the change in time. So this is a velocity. More specifically, it is a vertical velocity. Given x equals 4 and that dx dt is 2. Again, this dx dt is my change in x over the change in, let's say, time. So this would be our horizontal velocity. In other words, if we take a look at our parabola, there's my parabola there. If we look at our parabola, we are trying to find at x equals 4, we want to find the change in y. How fast is y changing? Given we know the change in x, how fast x is changing horizontally. So we want to find out how fast the y values are increasing at this exact moment. And that's really what a related rate does for it. It finds us an exact velocity at any given moment. So to do this, it's pretty easy. We have our equation, y equals 5x squared minus 6x plus 2. When we take the derivative, dy, now remember, we are doing the derivative with respect to t now, so this is implicit. So the derivative of y would be dy dt equals, this is the hard part, when we take the derivative of 5x, we're going to get 10x, but we get this dx dt minus 6. And again, the derivative of x, dx dt. So there is our derivative right there. Okay? So next, all we have to do now is plug in the values. So we're looking to find dy dt, so we can say dy dt equals, we can find dy dt, all right, that's my son. We get 10, we know x is 4, so I can plug in the 4, minus the 6, whatever dx dt is, and I think that was 2 here, right? And I can solve that, and that's going to give us 68. Whoops, because I forgot my 2 here too. Right answer sorry, my son distracted me there. So we got the x, which was 4, and the dx dt, which was 2. I forgot to tack on my dx dt. The answer is still 68. Luckily, I have my notes in front of me, right? Okay, so what this is telling me is that this is the change in the y values. And because it's positive, those values are increasing. So that's what we're going to do. We're going to write our answer now. You always have to write your answer as a sentence. This says the y values are increasing at a rate of 68. And that is what we would put. You always want to write a sentence for these. 1 point on my class at least. All right. So let's take a look at a kind of an application problem. So let's say we drop a pebble into a calm pond, so flat water. When you do that, the ripples from that pebble form concentric circles. The radius of the outer ripple is increasing at a rate of 1 foot per second. Notice the word rate. So this is a rate of change. In other words, it's a derivative for us. When the radius is 4 feet, again, so now it's not a rate, but this is actually a value, so we'll talk about that in a second. What is the rate of total area of the water changing? So they're looking for a rate right here of area. So the first thing we're going to do, and then you probably learned in your science classes, is we're going to list out all our givens. Now, where do you think they got it from? From their math. The first thing they tell us is that the radius is increasing. Now remember, this is a speed. It's like a velocity equation for us. So the first thing we're given is the rate of radius changing. So we're going to call that the change in radius. That's really what dr stands for. But it's per second, so that's going to be divided by some unit time. So dt, t for time. So the change in radius over the change in time, we're told, is 1 foot per second. And if we kind of notice here, this is kind of a cool little thing right here. This is for free. Look at dr is measured in feet. dt is measured in seconds. And that's really like why we really like this Leibniz's notation right there. It's very nice and usable. The next thing they tell us is the radius is 4 feet. And we want to find, I'm going to go write out what I'm going to find, the change in area. So dA stands for the change in area over a unit time. Change in area over change in time. This is what we want to find. And I'm going to list both of these out. The AP will give you a point just for writing that out there. So now we have to come up with an equation or a formula. And most of these tend to come from geometry. So we're given the radius, a circle, and area. So what equation has radius, circle, and area? Sure, area of a circle, which is pi r squared. So let's go and take that derivative. So now remember, before we do that though, remember this derivative right here, what this is right here is a position equation or value right there. So when I take the derivative of position, we know the derivative of position is velocity. So when I take the derivative of A with respect to t, we're going to get dA, the change in area with respect to time. Dat it, people. Yeah, get it? Dat it. Okay? Equals, be careful when you take the derivative of pi r squared. You're going to get to 2 pi r. But remember, it is implicit. So you're going to multiply it by the change in radius over time. So dr dt, dirt it. And again, what's really neat about this is now my velocity equation. This tells me how fast area is changing. It's like a velocity. How fast is my distance changing? And now we're ready to, again, solve this. So we would say dA dt equals 2 pi, the radius, which is 4, times dr dt, which we were told was 1, and we get 8 pi. So now we're going to talk about units, okay? The area, we find the change in area. This is why we like Leibniz. The top of the fraction is my area. Well, area here is feet, and because it's an area, we should know that that's going to be feet squared. T, the change in time, here is measured in seconds. So we are saying that the area of that ripple is increasing by 8 pi feet squared per second. And again, we're going to write that as a sentence. The area at, or I should say, whoops, let me just erase that. Or I should say, when the radius is 4 feet, is increasing at a rate of 8 pi feet squared per second. And that's pretty fast. What, 24 square feet? And that's only at that instant. What would the area be changing at when the radius is 5 feet? Well, then it would be 10 pi. So as we can see in this problem, the further we get from the center, the faster that area is increasing. This is an instantaneous velocity at this point. Very fun to do. All right, I normally tell a joke about circles here, but I won't, so I have this next equation afterwards to help us with that. Mr. Warnow, is full of hot air. He decides to blow air into a spherical balloon at a rate of 4.5 cubic feet per minute. Now, we're talking about a sphere, but if you notice right here where it says 4.5 cubic feet per minute, if you notice, and you should, this is a volume, but it is a rate. So this is our change in volume with respect to time. Again, this is a rate of change right there. We want to find the rate of change of the radius when the radius is 2 feet. So I'm going to list out all my givens. Okay, the first thing we're given is a change in volume, dV dt, is positive. It's 4.5 cubic feet per minute. When the radius is 2 feet, so the radius is 2 feet, and we want to find and we're looking to find the change in radius. So how do we write the change in radius? That's right, the change in radius. It comes from this, right? The change in radius, right? That's what the delta R stands for back in geometry. But we use dr instead because we're looking for instantaneous. So dr dt, that's what we're looking to find here. So let's go ahead and go to this. So we need our equation. Well, what equation or formula from geometry has spheres, radius, and volume? That's right, the volume of a sphere, which is 4/3 pi r cubed. Now again, we can kind of think of this as our position graph. This gives me my value. At any given radius, I can find my exact volume. But we want to find how fast that volume or that radius here is increasing. So to do that, we need the derivative. Anytime you see the word rate, you're going to derivative. I just made that up. So we get dv dt equals, then that's the 3. Drop your power like it's hot. We get 4 pi r squared. But don't forget, it's implicit, so we're going to get dr dt. And there's your derivative. Notice, make your paper nice. Start at the left and work your way to the right. And now I can plug in. dv dt is 4.5 equals 4 pi. The radius, which was 2, square that radius, we get 4 dr dt. So I solve for dr dt. You should be able to do this really quickly in your head. 4.5 over 16 pi. Notice I don't simplify it. You can if you want to. But I got to get my units. Dr dt, how are we measuring radius? Well, radius is measured in feet. Remember, radius is a unit, not like square unit, over the change in time, which is measured in minutes here. So now I got to write my sentence. It's positive, so we could say the radius when r is 2 feet is increasing at a rate of 4.5 over 16 pi feet per minute. Now, let's take a look here. When we score this, you need to have what's changing, how it's changing, and by what it's changing. Don't forget units. That's worth 1 point on the AP right there. All right, so we're going to take a stop here and go on to part 2, and we'll take a look at just 2 more examples there. Bye-bye.